We will now be studying 3 different examples to illustrate the use of the exponential form. Now just to do a quick recap, the exponential form is simply when we write z as r times of e to the power of I theta, and r over here refers to the modulus, while theta over here refers to the argument of the complex number z. So for instance, if I have z to be the complex number 5 times of e to the power of I pi over 3, then I know that the modulus of z will be 5 and the argument of z will be pi over 3. We are now ready to continue with example 19. In example 19, we will investigate how to compute the product of two complex numbers very quickly using exponential form. If you recall, what we learned in Cartesian form was that if I wanted to multiply two complex numbers z1 and z2, then I know this will be x1 plus iy1 times x2 plus iy2. And to do the multiplication would require an expansion of these two with the simplification of all the terms later on into the real component and the imaginary part, which was quite a troublesome thing to do. What we are going to see in example 19 is that the beauty of the exponential form would be that it allows for very easy multiplication of two complex numbers. So suppose the question was so kind as to give me the two complex numbers already in exponential form, and I was asked to compute the modulus and the argument of zw and z over w. Now using our previous knowledge over here, it would have been most troublesome and tedious. I would have had to expand this whole thing and then go on to calculate the modulus and argument. But now that I have the exponential form, I can just take zw to be z times w, and I know I can work it out this way. First, I'm going to pull out all the constants. Here I'm going to have 2 times of root 2. Then I know e to the power of a times e to the power of b is e to the power of a plus b. So using this idea, I can deal with these two components. E to the power of I pi over 4, e to the power of I pi over 6 means that I'm just going to add up the two powers. Okay, and I can factorize out I, which gives me this. Okay, and therefore I can arrive at the next step over here. What this tells me is that I have now written the product in exponential form once again, because I can see this is of the form r times of e to the power of I theta, where r is simply the constant 2 times of root 2 and theta is simply the angle up here, 5 pi over 12. The argument is therefore going to be 2 root 2 because it is r, while the argument is simply going to be theta, which is 5 pi over 12. So much easier than doing the multiplication. On the other hand, we could also calculate the same thing for z over w, and using the same properties, now I am going to take z divided by w, so I'm going to divide the two constants, which gives me root 2 over 2, or half root 2, and that tells me that the modulus of the new complex number is half root 2. Similarly, I know that e to the power of a over e to the power of b is e to the power of a minus b. Therefore, the new index of e will be pi over 4 minus pi over 6 times of I, which I can evaluate to be pi over 12i. So this part here is going to give me the argument, while the constant term here tells me that the modulus of z over w is just half root 2. As an exercise, I will leave it to you to work through the GC portion on the right hand side and to check that what we have obtained is indeed true, even if I were to use the GC to evaluate zw and z over w. Now let us look at example 20, in which we are given something slightly different. In example 20, I want to find the values of x and y such that e to the power of x plus iy can be written as this. Over here, I have something that resembles exponential form, while over here, this seems to resemble more of polar form. And from the polar form, I can see, it is almost polar form, but not quite. So let us consider polar form. Just says that z can be written as r times of cos theta plus I sin theta. Yet, over here what I have is a minus sign. Okay, so I can rewrite this. Instead of saying it is minus, over here I can write it as plus, because the negative of sine theta is the sign of negative theta. Okay, this is an important property that has cropped up a number of times. And also, cosine of negative theta is the same as cos theta. Okay, therefore, I can replace both angles by negative pi over 3. And reading off the polar form, I know that for this complex number, r is equals to 1/4 and theta is equals to negative pi over 3. How does that then help me? It tells me that in exponential form, I should obtain z to be r, which is 1/4, times of e to the power of negative pi over 3i. Now comparing this with e to the power of x plus iy, I can see that it is still a little bit different, okay, because I need to get out this constant and only have one term as the power. So recalling one of the properties, I can write this as e to the power of x times e to the power of iy. And therefore, comparing, I know that e to the power of x must be 1/4, while e to the power of iy, this tells me that y must be negative pi over 3. Okay, which is how I obtain this statement over here, as well as this. So from direct observation, I know that y will be negative pi over 3. But what about the value of x? If e to the power of x is 1/4, that means that x will be equals to ln 1/4. Or you can see this as negative of ln 4. Okay, because it is ln of 4 to the power of negative 1. I will now give you 10 seconds to try out part B, and we will continue when you have answered the following question. Moving on, now that everyone has tried, the correct answer is that, in fact, before I can write down the values of x and y, I need to first determine what is the value of r and theta. Okay, so it is not necessary for the complex number to be given to me in polar form as in part A. Rather, in part B, what I see is that it's given in Cartesian form, and I want to calculate the values of r and theta. Now this is a purely imaginary number, and it is a negative number, so if I were to draw my Argand diagram, I know that negative 8i will be somewhere here. Okay, it's a point that is somewhere here, which tells me that the modulus will be 8, and the argument will be negative pi over 2. So I can, in one step, write it in exponential form. So doing a simple comparison, e to the power of x times e to the power of iy will be 8 times of e to the power of negative pi over 2i, which tells me that comparing the constant portion, e to the power of x will be equal to 8, while if I were to look at the exponent over here, this tells me that iy is equals to negative pi over 2i. And solving this, I would be able to tell that x will be simply ln 8, which is equals to 3 times of ln 2, while y will take on a value of negative pi over 2. Finally, we are going to look at example 21 for one last case of how the exponential form can be useful in the chapter on complex numbers. In example 21, the complex number z is given to us in this form. It is one exponential form over 1 plus e to the power of I theta. And what I want to do is to simplify into this form, which says that z equals to half plus half tangent theta over 2i. Well, I need to find that in the end, there would be a half angle over here. So perhaps one of the best things I could do is to create the half angle first, okay, by factoring out the half argument. And what I can do is, I know that this can be written as e to the power of I theta over 2 plus theta over 2. Okay, that's the numerator, and hence I can rewrite it as this, while in the denominator I can rewrite it as this. Okay, and this is purely to create the theta over 2 because of the tangent theta over 2 in the question. Okay, now that I have the theta over 2, things are starting to look up because I observed that I can do a cancellation this way. And this leaves me with e to the power of I theta over 2 divided by e to the power of negative I theta over 2 plus e to the power of I theta over 2. And this looks slightly familiar. Now, if you recall in the first video for this lesson, e to the power of negative I theta plus e to the power of I theta will give me 2 times of cosine theta, right? And I actually proved this result for you. Now I have something similar. So what I can do is to use this property and convert this denominator into 2 times of cosine theta over 2. As for the numerator, I can convert it into this form because the numerator here can be expressed in polar form as cosine theta over 2 plus I sine theta over 2. Hence, I can convert into polar form for the numerator, and for the denominator, I use the property that I mentioned earlier. And now, I notice that I can split this into 2 fractions. Okay, and hence, I obtain this result. And then it is just a matter of very simple simplification, a cancellation over here. While over here, I notice I have sine over cosine, and thus I have arrived at my result.